Doing every challenge question part 51. This is Core Pure 2, chapter 7, which is on differential equations. This question is super confusing, if nothing else, because there is a typo in it, and this should say beta, not alpha. So that was annoying. But anyway, if you just investigate a to the e alpha x, now alpha is p plus iq. So you can just write that as a e to the p plus iq x, and then expand out the x, and also break this base down into a multiplication of two bases. So of course you can just add these two things up. So just doing that all backwards here. And now e to the px is just e to the px, but e to the iqx is of the form e to the I theta, and there can therefore be written as cos theta plus I sine theta, where it's cos qx plus I sine qx. Now, like I said, this should be a beta, so let's just pretend that it is. P minus iq can go in there, and then expand out the x and break it down again, like I did before. And then this can be written as cos minus qx plus I sine minus qx. Now, cos is even, so minus qx is nothing. Sine is odd, so this minus can be moved out to the front like this, and we can get this here. So that's all good to go. I think now we can just add these two things up and replace this with alpha and beta again, I guess. And that, of course, means adding these two things up. We can factorize out the e to the px, and then we can expand out the a into those two bits and the b into those two bits. Group up the cos qx's, and you get a plus b of them. And the sine qx's, you get a minus b, I, lots of them. And that's all good, because now if a plus b is c and a minus b is d, we're almost there, except this I is a bit annoying. And it's also telling us that c and d are definitely real, whereas a and b could have been complex. So how do we justify that? Well, it's because it says here, show that it's possible to choose a and b, such that we can do this. So what choices a and b can we make, such that this will definitely be real, and that this I will go away? Well, if you just choose them to be complex conjugates, a plus b is definitely real, because of course the imaginary bit will go away. And a minus b, like 3 plus 2i minus 3 minus 2i, is just plus 4i, like you just add the real bits together. Sorry, you add the complex bits together and the real bits go away. But of course, if that forms a number of the form ki, you can then times that by I, and it becomes, and the i's go away, and you definitely have a real number here as well. So essentially, just choose them to be conjugates, and everything will work out quite well. And that was the first question done. The second one is, okay, so we've got of the form, this is m squared plus 1, I guess we could write it as, just missing the middle term. Solve that for m is plus or minus I, which means is it the complementary function? I can never remember which way is round is which. Is this here, because it's just, if this is p plus minus qi, q goes here, but q of course is just 1, and then the p goes into e to the power px, but with that being 0, that doesn't need to be written, so that's just there. And now we need to choose carefully a particular integral that will work well for this. And I chose wrong first. I just chose something like this. I assumed, because it's not in the list, right? This kind of form isn't in the list. So I just chose this to work with to start with. Did some product rule to differentiate it, and then did some more product rule to differentiate it again. Notice how when you differentiate this one, you get lambda k e to the kx. And then when you differentiate the first half of this one, which involves just differentiating this x, you get lambda k e to the kx. So there's just two of those, and then the other bit is here. Anyway, when you put those together, this one and this one, to equal this, apparently. Now, clearly k has to be 2, but when you do that, you end up with this. And now I could choose lambda to be 1, I think. That would make this 5x e to the 2x, but then this would give me 4 e to the 2x, and that isn't, like, that's not represented over here, so that can't be correct. So I had to go back to the drawing board, and I decided to, take lessons learned from this, I guess, and say, okay, well, what can I do to improve this? Why don't I just tag on an extra e to the kx on the end, like with another unknown that can help me balance the equation at the end. So I did that. So let's differentiate it. Of course, product rule here, this goes away, and then the k comes down, and then this is just k comes down, and then differentiate this again. This is just k comes down, this is just k comes down again. This one needs some product rule, and then the first bit of the product rule will combine in with that, and you'll end up with two of them. The second one will just look like this, and then this looks like this, as I said. Put this and this together to equal 5x e to the 2x. Again, k clearly needs to be 2. That should be a k. That's just a mistype. Don't know how I managed that. Anyway, now it's a 2 because I've said k needs to be 2. And now we can just represent, okay, well, where are the x's in front of these here? Well, there's 4 lambda plus lambda of them, and that must equal 5. 4 lambda plus lambda is obviously 5 lambda, so lambda is 1. Put that in, and you get this, and now, obviously, these two things are balanced, so that's good. So we just need all of these things to be 0. So, okay, we've got 4 plus 4 mu plus mu equals 0. That means 4 plus 5 mu is 0. That means mu is minus 4/5. And that's all perfect. We'll put that information back in here, and we'll find a particular integral, and we'll combine it over with the complementary function, and we'll get our solution for y, generally speaking. Good. Now, we've got two questions here, which are super fun for people like me to do, because it's that time of the day where they just ask you something that's in FP1 or FP2. So solving differential equations via a substitution is just something that's in FP1. Therefore, I'm pretty comfortable doing this. And this first one isn't too bad. The second one ends up being a bit gross. But anyway, the first one's quite nice. So you have z equals y squared. So if we differentiate that with respect to x, we get dz by dx. And now differentiating y squared with respect to x, we get 2y, and then you can just tag on dy by dx, because this is just saying, essentially, I've differentiated y with respect to the wrong thing. Let's put dy by dx there as well. Now that's good. I can rearrange that to find dy by dx, and then I can put that in there. So if I divide by 2y, I get this. I can put that result into here, and I'll get this. And now, obviously, this 2 cancels with this 2. I can times this entire equation by y, and that's amazing, because now I can just shove a z straight in. And this here is an equation in terms of x and z instead. And then it says, by solving the transformed equation, find the solution in terms of y and x. So they want me to solve this first, get some kind of solution for like z equals something, and then substitute back in this y here, and I'll get in y and x. That's cool. Now this, I think you're supposed to use a one of those, what's it even called? The e to the integral of p of f of x integrating factor. Is that what it's called? But you can just spot here that this is just the result of a product rule having immediately happened. So because, this is the derivative of z, and this here is the derivative of x squared. Actually, you can also say it's the derivative of 1 plus x squared. You can just put 1 plus x squared together with z and say that's what happens when you differentiate with respect to x. So let's talk you through this. This is a product. So differentiating z with respect to x, you just get dz by dx and leave this one alone. That gives you that bit. And then when you leave this one alone and then differentiate this with respect to x, you get 2x, and you slam it there, and you get this here. Now, if we integrate both sides with respect to x to remove this d by dx, this integrated is just x plus c, obviously. Divide both sides by 1 plus x squared, and then y squared is z, so that's y squared, and then you can square root and you get this. Find the particular solution when y is 2x is 0, so put 2 here and 0 here, you just get 2 is plus or minus root c over 1, which means c is obviously 4. And yeah, then we can just put that value in there and we'll get the answer. So that one was quite nice. This one I think I made a complete mess of. I haven't really looked at any mark schemes. I know Solution Bank will probably have a different idea, but I just did something and it worked, so I decided to keep it. It's probably not the optimal way of doing it though. So what I did was I first said, well, u equals log of x based on this, and then I differentiated this with respect to y. So both sides differentiate with respect to y, so it's du by dy, and then differentiate that for 1 over x, and then say, okay, it's dx by dy, because I'm supposed to be differentiating with respect to y. So okay, I did that. And then I said, okay, well, I can just turn all of this over to get dy by du equals x dy by dx. And that's fine, because now I can substitute this result into here. So this is dy by du times 1 over x equals dy by dx. That would be very nice, because this x would then cancel with it. The tricky bit is trying to get to d2y by dx squared. So that was the tricky bit. I also wrote this as e to the power u. I think I was going to do something different, actually, but I don't know whether I ended up using that. Anyway, I'm going to take this equation here. Yeah, I am going to use it. And I'm going to differentiate again with respect to u. So this differentiated with respect to u is obviously this. This differentiated with respect to u, we need to do a product here, right? So this differentiated with respect to u is just e to the u, and leave this one alone. And then leave this one alone. And now this differentiated is just d2y by dx squared. That's differentiated with respect to x. But because I'm supposed to be differentiating with respect to u, I'm now going to tag on a dx by du afterwards. In the same way that here, I was supposed to be differentiating with respect to y, so I just differentiate it anyway. This is here just differentiating it anyway, and then saying, well, I differentiate with respect to x, and I was supposed to do it to y. So here, I did it with x, I was supposed to do it with u. So that's kind of how I think of it in my head. Anyway, this actually turns out quite nicely, despite the fact it looks like a complete mess, because dx by du is clearly from here, e to the power u, just differentiating both sides. So I can put that result in there, and then e to the u times e to the u is e to the 2u. So that's all good. And now I can rearrange this for d2y by dx squared by just moving this stuff over to the other side, and then dividing by e to the 2u, Of course, that just makes e to the minus 2u here and e to the minus u here, and that's that. And I can put that result into here, except x squared just happens to be e to the 2u, squaring both sides of this, which is fantastic, because that means when I times this by x squared, this thing here, which is this here, when I times that by x squared, the e to the minus 2u's will go away, and this will form a nice e to the u again. So I'll end up with this here. And then, of course, x is e to the u, so I'll put that there. And now dy by dx, I've got way back here, dy by dx was 1 over e to the u dy by du. So first I'll put those two things together, but I'll also say dy by dx is this thing here. These two things cancel, which is fantastic. Ln x, by the way, is, of course, just u, so I've put that over there. And this looks like a nice second-order differential equation that I can just solve, right? It's m squared plus 3m plus 2 equals 0 for the complementary function. M is plus or minus, or is minus 1 minus 2, I guess. So that's great. So we have solutions of the form this to start with, because they're just real, so it's just going to be of the form this. And that's good. Now I need to work on the particular integral. So when you have something like this here, you just need to make a linear guess like this. I regret choosing mu because it looks way too much like u, but who cares? Differentiate it for lambda, differentiate again for 0. Put that result into here. So obviously we get 0 here plus 3 lots of lambda plus 2 lots of this, make u. And now we can just solve this. Clearly, lambda has to be a half for the u's to match both sides. And if lambda is a half, that's 3 over 2. And this whole thing has to be 0 because there's no constant over here. Well, 3 over 2 plus 2 mu equals 0 means mu is minus 3 over 4, I think. And we can put those results back into that, and we can combine them together. And I think we get this as our function of y in terms of u, which isn't what we were asked. So now we need to fix that as well. But that's not too bad, because we can now, the original thing was x in terms of y, or y in terms of x, right? So we can replace this u with log of x here, here, and here. And now put this minus 1 up to the top here using power law for logs, and same for this minus 2. And now the e and the log can cancel each other out. And we'll just get a x to the minus 1, which can be written as a over x, I guess, and b x to the minus 2, which is b over x squared, I guess. And this will be our answer. And then it says, find the equation of the curve passing through 1, 1 with gradient 1. Now, that's essentially using this, but actually solving for a and b now. They're just giving us the data to find a and b. So this tells me x is 1 when y is 1, when dy by dx is 1. So, okay, if you just put in x is 1 and y is 1, you get, also I made a note here, this tells me that u is 0, but I'm not actually going to end up using this. I thought I could use one of the previous results, and then I worked out it was not easier to do that. It was easier just to use this here, which is probably why they gave it to me. Anyway, put in 1 and put in 1 and put in 1, and you get this. Log of 1 is, of course, 0. Add 3/4 to both sides, you get this. And then why does this dy by dx help? What are you supposed to do with that? Well, you're supposed to take this and just differentiate it all with respect to x. To get this, of course, this is ax to the minus 1, so the minus 1 comes down, lowest term minus 2, and so on. This differentiates to 1 over x, as we've seen before. This just goes away. Put in 1, 1, and 1 here. There's nowhere to put this 1 actually here, so I'll just put x is 1 and dy by dx is 1, and you get this here. This turns into this. You can do, I guess, what, this one minus this one to get this, and then put that result into there. And I think a is going to have to be 16/4 to make that balance, yeah, which is then 4. And then you can put that result into your answer there, and you'll be done with this question. Just a really nice question there.